There it is.
All right.
Hey, Dad.
Oh, son, how are you?
Good. All right, so we're making parts. These, if you push down on it, Dad, other way, there you go. These are the wings, the skins for the horizontal stabilizers. Okay, there's this one, and then there's this one. So there's one is basically top and bottom. These two assemblies are bilaterally symmetrical. So it's a symmetrical airfoil. It's in a 6 series. It's like a 10% section 6 series NACA airfoil. One of them has a joggle, and the other one does not have a joggle.
What's a joggle?
Joggle is just a lap joint.
Okay.
So what's going to go on here is that there's a tip rib, there's the main spar, there's a front rib, and then there's a rear spar. And then they fit into the skins. The next thing I'm going to do, I have to remake this. You'll see Bondo on here. I wasn't satisfied with the fit of my first part. And so I put some tape down into the mold to make up the thickness of the skin. And then I put finish putty down. Finish putties are a great way to capture a surface. Bondo, not so much. Bondo's a little too porous for that, but the finish putty works really well and it releases beautifully. And then I made a new mold that has a little bit better profile. Requires very, very little fill. So I have to make another one of these.
Is that the mold for the end piece there?
Yeah, this is the mold for this part. This part made this mold. Okay.
Good.
So I'll have this profile and the same structures, and they go in like that. And then
these are the ailerons?
these are the elevators, and they're all flying elevators. Okay, there's not like an elevator. It's a horizontal stabilizer that's full flying.
Okay.
I chose that because it's a little bit easier than trying to figure it out. Also, there is the potential of this being in the transonic range, and this is how you get away from Mach tuck in the transonic range. If somebody puts the nose down on this thing and it gets up to its critical Mach number, which is 0.72, this is a safety feature.
I'm presuming that's a very high number.
It's a reasonably high number. It's certainly in the transonic, but that the airfoil I've chosen is a low transonic airfoil. It's 0.72 Mach. That's
across trans is across.
So there's the part of the air that's uncompressible, and then there's the part of the air where you're starting to go fast enough to where you're starting to stack it up, actually starting to create pressure. And that's the area we call transonic. Once you go past that, that's supersonic, and you're actually pulling shock waves. It's a straight up analogy to what's going on in the bow of a ship. All right, if you're below the hull speed, you're not pulling any bow wave. You're in the port, and you're going very slow, and you're just making some ripples that go out. As you go faster and faster, you start to catch up to the wave speed in the water, and then it starts to drag a wave off the front, and that's really good analogy of what happens in the transonic and supersonic realm. This is a low transonic shape.
Which means it's not going to be super fast.
It is not going to be super fast, but it's going to be pretty damn fast. It's designed to be pretty damn fast, but not super fast.
Not fighter jet.
Not fighter jet, but fast. World War II era fast. Okay, and these are things they worked out in World War II in terms of what. This is a way of preventing Mach tuck.
What?
Mach tuck. Look it up. Some of you know. Mach tuck is where when a World War II fighter would get transonic, usually in a dive, it would start to form shock waves on the outside of, well, right here. It would form shock waves on the outside of this shape, all right, where it gets thickest, because it's speeding up, right, and it gets to that point where it goes past the speed of sound. And then if you have the hinge control surface. It usually hang right off of this hinge control surface, and it will blank that hinge control surface on the backside of that shock wave. And then you don't have any pitch authority, and you make a big smoking hole.
Is that when they got into those dives they couldn't pull out of?
That's right. So that's when they started to figure out what this was, and the solution was an all-flying tail. That's why this has an all-flying tail.
All flying, which means
The whole thing moves. Yeah.
Instead of just two flaps.
Just a flap. Yeah. So that was the critical design characteristic of a tail that is safe in the transonic realm. Okay.
Cool.
So that's why I did this. That's one of the reasons. The other reason is that it is pretty easy, right? I just have to work out this hinge point, and that hangs onto the back of the fan casing, right?
Which we'll get to next.
We'll get to that next. But so this is the lamination as it comes out of the mold. Now this, I talked about peel ply in the last episode, and you don't have to use it. Well, this is an application to use peel ply, simply because I have so much of this area that I have to prep for bonding, right? And it just was easier for me just to cut a chunk of peel ply and put it down over the whole thing. I don't necessarily need it here, but I do need it in these areas.
Does that stand for peel it and ply it?
Yeah, okay, so peel ply is just this stuff. We call it peel ply because you peel it off, right? But it's Dacron cloth. It's Dacron sailcloth. And it leaves a very nice finish on the inside. It smooths things out. And for me, I use it as a good way to prep for bonding. I don't bond straight to peel ply, to a peel plied surface. I do a prep, 60 grit, sand. You gotta be really careful with 60 grit because there's not a lot of material here. You can't afford to go through it. And then isopropyl alcohol clean, never touch it again, and then you're ready to bond. But that's just what I do. Some people use acetone, those things are acceptable. There's a lot of literature on this. Everybody's done their own research, but this is about where it all fell. 60 to 80 grit, some people will use, Scotch-Brite pads. I'm not comfortable with that. I do a sanding. Right, 40 grit, 80 grit, somewhere in that range. But you got to do your own testing. Anyway, these will get bonded up. I'm going to use Flox and my laminating resin. I use Flox and laminating resin when I'm bonding like materials. These are all the same material, so I'm using the same resin system, has the same coefficient of thermal expansion. You put flocked cotton in it. It is a tried and true tested way of making this sort of bond. When I'm bonding in between materials that have different coefficients of thermal expansion, different properties, I'll use a proper structural adhesive. So the hard points in here will be bonded in with a structural adhesive, but all of this work I'm just going to do with Flox. So my next step is I got to make this part. I got to evaluate it. I'll put it in here for fit, and then I'm going to make one of these. And then I'll evaluate it, I'll weigh it. I'll see if I want to make any further changes before I commit to another 4. Okay, so and then I have these ready to go. This one I'm happy with. These I'm happy with. 4 years ago, I forgot what my lamination strategy was for my tooling strategy. I ended up killing myself here trying to do this, and I had to do a bunch of fill work. Now, the way to do this is I forgot. I was just going to do it this way, just with some plies up the side, and then do flat stock on the back side. That's a great way to make a mold like this. So I had to transition all these molds from here. I had to cut this side off and then put these in.
Looks nice and clean.
It makes a nice and clean part, and I think I'm actually going to do that with this one. So I had to iterate on this mold as well, but it's making nice parts now. The spar is this. I went back, did some math, figured out I can make it a hell of a lot lighter. And this one's 11. Yeah, this is the one I figured it was just too heavy.
Yeah.
Yeah.
So how many plies is that? You had 4 or something on the other one.
Yeah, I think I had 6.
6.
I went back, did some math, realized I could do it with 2 uni.
Looks good.
This is 11.8 ounces.
Yeah, it was something like.
It was almost a pound, which is.
A pound last time somewhere. Maybe.
I will never get to where I want to get with this if I don't look at every part and look at it critically in terms of how heavy it is and what I really need and what I think I need when I'm sitting at the computer. And those two things are different. People sometimes don't understand. When you get it, you get that part in your hand, and you're like, man, I can lift a truck with that, you know. Yeah, the load case I'm working off of here is 500 pounds. 500 pounds at mass at aerodynamic center. Okay, and there's an equation for that. I'm not going to share it, but it's the coefficient of lift, and there's the equation that states in there. But and it has to do with the speed. But basically it's maximum lift coefficient, and bottom line is it can make 500 pounds of lift. So that's that times the safety factor, and that's what I'm working off of.
Available math for all this stuff.
It's been worked out for 100 years. Yeah. I'm not reinventing the math. I'm just taking it out of books, putting it on a spreadsheet, and applying it. Yeah. I've understood that stuff since I was in high school. No, I've looked at these shapes. I know what these shapes do because I've looked at the results of these shapes. If you want to understand airfoils, get the NACA book and go, right? You see the curves change with the shape, and you understand what the shapes do. Okay, just take it and go, just like a flip book. Oh, right. So we'll go over here, Dad. So the other thing that's going on right now is that I'm making a bonding fixture for the fan casing. I want to get parts bonded up this week if I possibly can. So this is the outer casing of the fan system itself. If we'll come around here, Dad, I'll pull this part. I'll pull this.
Get over here somewhere. Get some
Yeah.
through.
So the fan casing is laid out in quadrants. That way I can tool it in quadrants, okay? Because there's also a lot of stuff going on the inside, right? These are all designed to lock together, and when they're bonded together, they're going to be extremely strong. But what it does is it creates the fan casing for the fan itself, which is sitting over there, okay? It creates the stator, for lack of a better term. This would be called an NPL straightener. All this does really is straighten the flow. All right, this is not a compressor. This is an air mover. It might make 1.1, pressure ratio 1.1 if I'm lucky. The idea here is not to compress the air. The idea here is to move the air, right, and as efficiently as you can. And losing power in compression is the way to make this really terribly inefficient, right? So I have to fight for everything to make this whole thing work. But all this it does is straighten the flow. Whatever swirls in there, and there may not be very much swirl, will get straightened out by these stators, and then it will go out of this ogive. And the cone here is a pressure recovery shape. It looks like a Hershey Kiss. The Hershey Kiss shape, people in the Long Easy community know what I'm talking about. It's called a pressure recovery shape. It takes the flow in the transitional and the turbulent zone where you get high pressure, and it, because of the shape, it pushes and creates a thrust vector, and it just negates some of the drag.
That's the push on the plane then.
It negates it. It helps offset the drag. It doesn't eliminate the drag, but it reduces the total drag coefficient. So between that and how it interacts with this shape here, there's a crest here. There's what I call an ogive. This will come out and create a convergent duct where this area is less than this area. It can cone in and make it the same area, or it can cone way in and create a divergent duct.
What's going to move it?
A linear actuator. It will be buried inside of, it will live in here.
And you'll be lever attached to it or something that pulls it in and out, or what?
So it slides on the central shaft.
On its own?
No, so this slides on the shaft,
Yeah.
and then it's being pushed by a linear actuator.
Okay, you will have a linear actuator. Which
Yeah, it will be
cause
buried
it,
in
which
here.
you-
Yeah, it'll be buried in here. You won't be able to see it.
Push the lever, shoves it up.
That's right.
Back, so
That's right. So yeah, that's how I imagined all of that going together, and what that does is widen the area, or the performance area where this has efficiency. All right, you want a divergent duct when you're at rest or at slow speeds, and you want a convergent duct when you're at relatively low power settings at cruise, or but all of this, we're going to have to figure that out. We're going to have to go and run it and see how much this really.
if I'm seeing this right, it'll be your speed, your thrust, it will be a combination between your throttle and this.
Yep. It's what RPM, how much mass flow, what the velocity component is. All of that changes constantly, and so this is a way to broaden the area where this has
Does
efficiency.
this take the place of propeller pitch or that sort of thing?
Kind of. I don't think it's going to be quite as
But
good as
that's
that, but
basically-
yes,
it
this is what
basically
yeah,
does.
yeah,
Cool.
yeah. So that's how that works. Now, this part, yeah, it's all messy, but this will get it all bonded together, and then there'll be a hard point in here, and I may have to go back and laminate this, but I'll probably end up with an aluminum hard point in here, and this is going to pick up. This is a hard interface to the airframe structure.
And if they picture this on the back of the airplane, that's what you got. This
That's right, and yeah, and then the fan casings go on the outside of that, and these parts, these are the molds for them. These are the caps that go on about right here. Okay, so these are structural caps that tie in the horizontal stabilizers. So there'll be a hard point in here, and then this will bond onto here, and it will triangulate this, actually create two box sections. One box section per side. It'll pick up this flange, bond here, and bond on to here. And it will create an extremely strong torsional box that will take the flight loads there and all of the bolt interface. This is where the two on the sides is where the horizontal stabilizers bolt on. The one on the top is where the vertical stabilizer bolts on, and then it bolts into the fuselage at the bottom.
So those stabilizers will bolt to this.
Yes, they will bolt. There will be a buried bushing in here, and yeah, that's how that works.
The rudder or the
Yeah,
top one.
rudder. Yeah,
would be.
It'll be a split
would be
rudder.
The third one. Yeah.
Yep, the third one on top, and then the one on the bottom bolts into the fuselage, and yeah, that's the scenario. So this is all structural, and it's all integrated into the airframe. It's not like you slap a fucking turbine onto it. This is all very integrated into the airframe, and it's one of the ways I can save weight, right? By using this as a structural member in the airframe. So
Cool.
anyway, that's what's going on here. It's kind of like everything, everywhere, all the time, but
It's coming together.
it's coming together. I'm really tired of just having parts. I'm very glad to have made some OML parts, but I want to have these put together. So that's next. Next is starting to bond stuff up.
Okay.
All right, that's about it for today.
So just good.
All right.
Son. Good job, son. Thanks,
All right. Sorry for you wearing a dojo shirt. All right, Dad.
You can
Bye.
put what you want in there or not.
All right, bye.
It's too goofy. Take it out.
All right, bye.